This is our next video on Hess's law, where we're going to look at a past NCEA question. I'm pretty sure this is from 2016, where we've been asked to find the enthalpy of combustion of methanol. They give us everything in purple here, so they give us the equation with states of matter, you'll note. They'll give you the values for the enthalpy of combustion of carbon, enthalpy of combustion of hydrogen, the enthalpy of formation of the original substance, which is methanol. Because these aren't all enthalpies of formation, we can't just use our enthalpy of formation calculation. We have to use Hess's law. So the first step in a question like this is to turn these equations here into, these values here into equations, balanced equations. Now just remember that enthalpies here at the little circle, standard enthalpies, have to have 1 mole. So whatever is in the brackets there, you can only have 1 mole of in your balanced equation. If you double the number of moles, then you double the enthalpy change. So make sure you've only got 1. This means you might have to use halves or thirds of things like oxygen, because it's O2, to balance it. Let's go through this and see what happens. So, the enthalpy of combustion of carbon means burning 1 mole of that with oxygen gas to completion. So in this case, to carbon dioxide. So we've got that, and you'll notice that I'm keeping the enthalpy changes next to these as well. The reason for that is going to be important in step 2, which is probably the hard bit of this. My enthalpy of combustion of hydrogen, this one's a little bit harder to balance, because you have to use a half mole of oxygen to make it work, because water only has 1 oxygen atom, so therefore for 1 mole of hydrogen to be combusted, you can only have half a mole of O2, and that is negative 286 kilojoules per mole. Now if that doesn't sit well for you, then by all means, but it makes it hard, double this, but it means doubling the enthalpy change as well to be 572 kilojoules per mole. Then our last one is the formation of methanol. That means making it from its elements in their natural state. So that means solid carbon, hydrogen gas, and oxygen. Again, with only 1 oxygen atom, it means half a mole of O2, and that's negative 240. The next thing is to compare those equations with our original equation. And our original equation has got 1 carbon dioxide, so we know we're going to need 1 of those equations, 2 waters, so I'm going to need 2 of this equation, and it starts with 1 methanol, so I'm going to need an equation with 1 methanol in it, and I do have that. Problem is, it's on the wrong side. This is a product, and we want it to be a reactant, but we're allowed to flip that around. If we change the direction of the arrow, or flip this equation around, we have to change the sign of our enthalpy. It goes from being exothermic to being endothermic. So let's have a look at step 2, where we have done this comparison. The first equation was just correct because it had 1 CO2 in it, so I just leave that the way it is. My original equation had 2 H2Os being formed, so I need to double this equation, and as I said before, in doubling the equation, I also double the enthalpy change. It also had methanol as a reactant, not a product. So I've actually flipped that equation there around, so it reads the other way. In doing so, I have actually gone from it being exothermic to being endothermic. So I've multiplied it by negative 1, basically. I've flipped it around. Once I've got those, I'm ready to do step 3, and all that is adding up this value, and this value, and that should give me the enthalpy change for this equation. Bear with me, I'm just going to change my whiteboards over because this didn't fit on one, the size of my writing. Let's see if I can do this without too much issue. There we go. So step 3 is adding up my enthalpies, and I've done that. And I get negative 726 kilojoules per mole. Now, when you're learning to do this, it is a really good idea to check your answers. And the way you check it is you do those equations again, like we've done here, and we start seeing what cancels out and what adds up together. So what I've got here are the three equations that have given me that enthalpy change. And I notice that if I put them all together, my carbon gets cancelled out because it's in two equations, and one's a reactant and one's a product. If something is a reactant and a product, and there's the same amount of them on each side, they cancel out. They don't appear in our final equation. The same thing is true for H2. And that's just as well, because my final equation didn't actually have H2 in it. It had 3/2, or 1.5 oxygens. But what I notice is I've got 2 over here. But that's okay, because I've got a half over here. And 2 minus a half is 1.5. So here would be my equation as it is. Reactant, product, so I can take away half a mole for each of them. And so sure enough, I've got my methanol, follows all the way through to my final equation. That's what they gave me in the question, good. My 2 minus a half gives me 3/2, or 1.5. That's what they gave me in the equation. My 1 CO2, that's good, and my 2 H2O. If I went back to the original question, which I'm about to do now, we will see that it's exactly the same equation. There we go. So that's my check. Now, if I don't have time in an exam to do a check, I just have to trust that my steps 1, 2, and 3 were correct and just move on. I'm going to show you a harder example in the next video, because which is probably about as hard as they get, but this is a very typical NCEA question for applying an understanding of Hess's law.